Hi everyone, my name is Rahil. Thank you for viewing this talk. In this talk, I'll tell you about my work with David Paganin on active wave particle clusters. So, back in 2005, Yves Couder and colleagues in Paris discovered that if you take a container filled with silicon oil and you vibrate it vertically, then you can get a droplet of the same liquid bouncing and walking horizontally on the liquid surface. So, as you see in these top videos, each time the droplet bounces, it creates a localized, damped, standing wave on the liquid surface. The droplet then interacts with these waves on subsequent bounces to propel itself horizontally. So the smaller droplet you see here on the left is known as a walker, and it arises at single frequency driving, whereas the bigger droplets you see on the right are known as super walkers, and they arise at two frequency driving. So three key things to note about this system. So the first is that the droplet and its underlying wave, they coexist as a wave particle entity. So if there was no droplet, so if I were to poke the droplet, the underlying waves would decay completely and the liquid surface would become completely flat, right? So the wave and the particle here, they coexist. Now the second point is that the droplet is active in the sense of an active particle, because even though the entire liquid surface is being vibrated vertically, the droplet locally extracts that energy through generation of these waves, and it converts that energy into horizontal self-propulsion, right? So the droplet is an active particle, and in this case an inertial active particle. And then lastly, there is memory in the system. And this is because the disturbances created by the droplet on the liquid surface, they decay very slowly in time. So the droplet is not only affected by its most recent wave, but also by the waves it created in the distant past, right? So hence there is memory in the system as well. Now, interestingly, these droplets have been shown to mimic several behavior that are usually thought to be exclusive to the quantum realm. Now, a widely used mathematical model to describe these walking droplets was developed by Anand Oza and colleagues in 2013, and it's known as the stroboscopic model. So to understand this, let us look at the experimental video here shown. So this experimental video was created by only taking one image of the droplet per bounce. Hence, you neglect the vertical bouncing dynamics and you only see the horizontal walking dynamics here. So this is exactly what the stroboscopic model does, that it averages over the fast vertical bouncing timescale, and it averages over that, so you get an equation of motion for the horizontal dynamics of the droplet. So the equation here is essentially Newton's second law, F equals ma. So on the left side you have an inertial term, there is dissipation in the system, so you have a drag term, and the complicated looking term on the right hand side is the force that the droplet feels from the underlying waves that it creates. So the key thing to note is that the force on the droplet from the underlying waves is proportional to the gradient of these waves, and because these waves decay slowly in time, you have to integrate over the past history of the droplet to take into account all the waves. Now, if we look at the wave field created by an individual droplet, then it has features of spatial oscillations and a spatial decay, right? So one convenient choice of this waveform is a cosine function times a Gaussian decay, which captures spatial oscillations and spatial decay. Now, if we non-dimensionalize the equation of motion of the droplet, then we get two dimensionless parameters here. So one is r, which is the dimensionless wave amplitude of the droplet generated waves, and the other is tau, which is the dimensionless wave decay rate, or in other words, the memory of the system. So if we fix r and vary tau, then at low memory, we have a stationary state of the droplet. So this is a droplet simply bouncing and not walking. And as we increase this memory parameter tau, then at some point we have a critical value of memory where we have a pitchfork bifurcation and the stationary state becomes unstable and we get a steady walking state of the droplet. And this is what we usually see in the experiment, that the droplet walks steadily across the horizontal liquid surface. Now, if we have multiple superwalking droplets, then we see some very interesting behavior. So at low memory, they collectively self-organize into a crystal-like lattice structure. As we increase memory, the crystal disintegrates, but the droplet remain bound and they oscillate chaotically. And at high memory, the bound state completely disintegrates and the droplets behave like a gas of particles colliding with each other like billiard balls. So inspired by this dynamics, we decided to use the stroboscopic model and extend it to multiple droplets to understand the dynamics that we get when you have multiple droplets interacting with each other. So in the stroboscopic model, we now have two new ingredients. So because we have multiple droplets, each droplet does not only feel its own waves, but also the waves created by the other droplets. And the other additional force that we have is that if the droplet get too near each other, then they'll feel a short range repulsion force to take into account the finite size of the droplet. And if we do this, and if we start multiple droplets in vicinity of each other, then we find that these droplets self-organize into a cluster. So as you see here, in the cluster, at the center of the cluster, the superposition of all the waves created by the droplet generates a potential well, and then surrounding this potential well, you have a wave barrier. And again, this structure kind of emerges from the superposition of the individual waves created by the droplet. Now, with increasing memory, we find various types of collective excitations, and I'll show you three examples here. So one type of motion we get is surface oscillations, where the droplets in the core remain stationary, while the droplets on the periphery oscillate azimuthally back and forth. We also get what we call the compression mode, where the entire cluster oscillates between something that looks circular and something that looks elliptical. And we also find rotating modes where the shape of the cluster remains elliptical, but the angle or the inclination of the major axis, it rotates with time. So in addition to the periodic collective excitations, we also find irregular chaotic modes as well. So as you see in the example here, we have intermittent rotation where the droplet cluster changes its chirality from rotating clockwise to counterclockwise intermittently. And for smaller droplets, we find another type of chaotic motion where, as you see here, the droplets are moving chaotically within the cluster, but in addition to that, the center of mass of the cluster is also moving around, and we find that this motion is diffusive on longer time scales. So from these observations, we can draw some similarities with nuclear physics. So the different collective excitation modes that we see, such as these different vibrational and rotational modes, they are similar to the different excitation modes that are observed in different models of nucleus, such as various vibrational and rotation modes. Now, interestingly, if we calculate the time average wave field in these dynamically distinct excitation modes, their time averaged wave field are more or less the same, and the overall profile of these time averaged wave fields is not too dissimilar from what you see in a mean field model of a nucleus, where a single nucleon fills the potential of the entire nucleus, and the potential that's usually taken has a similar shape where you have a deep potential well in the middle, supported by a bulge or a barrier on the outside. Furthermore, we also find regimes where the chaotic cluster can eject single particles, and if we do statistics of this particle ejection by looking at ensemble of initial conditions, and looking at the time taken for the particles to decay, then we get exponential decay, again very similar to a radioactive nuclear law. And lastly, there are more exotic nuclei in nuclear physics, such as halo nuclei, where in addition to the core nucleus, you have nucleons hovering around it. And in our simulations, we find that we can have a similar regime where, apart from the core cluster, we can have individual particles trapped surrounding this cluster. Thank you for listening to this presentation. Here is the paper relevant to this talk. And if you have any questions, feel free to contact me on my email address. Thank you.